Hello everyone and welcome to my next video, this time covering the topic of structured exception handler overflows using an Egg Hunter payload. You should already be familiar with the structured exception handler overflow technique. If you are not, I would recommend to have a look at my previous video. It's about 16 minutes where I will explain to you the technique in more detail. This time in this video I will just roughly go over the technique and will more focus on the Egg Hunter. Just as in the last videos, if you want to follow along, go to the exploit database, look for, this time for the Easy File Sharing web server, click on this application icon, download the executable and install it in a Windows machine. What we will need for this session is a Kali machine, which will act as our attacking machine, and our victim machine. As you can see here, I already installed the Easy File Sharing web server and it's running on this IP address. Before we start anything, we want to make sure that the network connectivity is set correctly. To do so, I just tried to reach the web server and as you see, it is working. So, we will start here with a skeleton Python script I already created. It basically consists of a socket connection, of a network connection that will be established to our victim Windows machine on port 80. And I created a payload. To get a better understanding what you want to set as a payload, I created an example connection. So I used Wireshark. I connected to the target with my browser, and this is what was sent from my client, and this was the response from the server. We don't know exactly where the buffer overflow will be, but we will just try with the first parameter. Instead of asking the web server for favicon.ico, we will ask for a file that consists of 5000 A's. So I prepared the first crash. We have A times 5000, so we will add it here. We will add plus crash 1. And we will rebuild just until the user agent. This will be enough to get a valid connection. We save it. We open our debugger, we attach it to the web server. We make sure it's running and we send our first payload to see if it's working. Python skeleton. And as we can see, we have our first access violation when reading 41.41.41.8d. And if we scroll down the stack, so we can here already see the A's, it looks like there's an SQL table in the background of this web server, and it's making a query to find the website it wants to deliver. And it looks like the file name can be as long as we want it to be. And if we scroll down here, we see all our A's. And what we want to reach here is we want to override the next SEH and the first SEH. If you remember from the last video, what we want to do is the first SE handler should point to a pop-pop-ret instruction. The return will make sure that we come back to this address. Whatever we write in here will be executed, so it will be treated as assembly codes, as opcodes. We want to put a short jump in here to jump, let's say 6 to 10 characters, bytes further in our stack. Here we want to put our payload that gets executed. So now we will do exactly what we did in my previous video. We will create a cyclic pattern to figure out after how many bytes we overwrite the next SEH and the first SEH. We will search for a pop-up-ret instruction, so we return to this address, and whatever we write here will be treated as assembly opcode, so not as an address. What you write here will be executed. We will write a short jump to jump over the SE handler into this area, and instead of the A's, we will put some knobs to create a knobsled. I will fast forward what I do now, because I assume you already know these details. If not, I would really recommend to have a look at my previous video. now that we have a working SEH code, it would be the right time to replace our knobs with a working payload to get data execution, to get a shell or something. I have to be honest, I tried for at least 1 hour to find a payload that works here, but for some reason there must be some kind of bad character or something. I can't get the payload executed, and also it fits pretty good for this example. We want to do some egg hunting, so instead of putting a reverse shell or something right in here, we will put the egg hunter in here, which is very small, and we will try to find another parameter or position where we could put our final payload. To do so, let's have a look at our script again. And what we see here is we have another parameter, for example, the user agent, where we could put a payload. Let's just try it, and instead of sending a user agent, we will send a cyclic pattern. We would just call it crash2 in here, and we will use a new Mona command. I mean, it's not new, but I haven't used it before in my previous videos, which is find an MSP. And what it does, I will show you right away. So let's once again put our cyclic pattern in here. We already have it in our file. If not, use Mona pattern create, I don't know, 5000, or we don't need that much. I will just copy it, pattern. Put it in our crash2. Let's save it, restart this application. So what find MSP will do is it will look for cyclic patterns in memory and will tell us if it found it and how many bytes it found. We will nevertheless send again our breakpoint. We will run the program. We will now send our payload. We cause the exception, Shift F9. We do the pop red, pop red. We have our jump shot. We are in the knob slot again. And now we do the Mona find MSP. So as it says here, it looks for cyclic patterns, and it found at least 3 positions. It will now take some time, because as you see in the last line, it will walk the stack to see if it finds even more. So while this is loading, we can already get rid of the cyclic pattern here, because we know this will be our payload. So now one specialty, when we write our egg hunter, our egg will be a 4-byte string. So by default, if you use Mona to create one, the egg will be WOOT. We will put it in front of our second crash. So our egg hunter will now search for this WOOT. What we will make to ensure that the egg hunter won't find itself, because we will also have the egg at least one time in the egg hunter, we will write the egg here 2 times. So the egg hunter will just find something if it's 2 times the same egg in a row. There will be several occasions where it will just find itself, so it will just find 1 egg, but then it will just continue. Okay, are we done? Now we can just crash it. It was just important for us to see that at some point in memory. Okay, now that we have proven that we have control over the SEH, and we have a second parameter where we can put our second payload, the shellcode, including the egg. Let's now create our egg hunter using Mona again. So let's first have a look at the parameters, Mona help egg. So with T, we can set the egg, or here it's named the tag. By default, it's WOOT. The next parameters, C and F, they kind of work together. So if you create a file containing the shellcode, with -C, you will create a checksum over the shellcode. So this will ensure, let's say you have multiple places in memory where the shellcode is stored, and some of these places are corrupted. So this would mean that also the checksum would not be correct. Here the egg hunter would also compare the checksum to the original one and will just execute the payload if the checksum is correct. If you later on want to fine-tune where the egg hunter should start searching for your second payload, you can do it with a start rec. And if you're using, or if your target system is a Windows 64-bit system, you should use WW64. If not, if it's just a 32-bit Windows, you don't need any additional parameter. It is important that you know your target system, because the egg hunter will later on make use of system calls to verify if a memory address is readable or accessible or not. And the system calls are handled differently between the operation systems. So if you attack the wrong operation system, your egg hunter might fail and the program might crash due to an access violation. Okay, let's now create our egg hunter. So we will just use Mona egg. We will copy the egg hunter from the file. We'll place the egg hunter in here. And we will adjust our first crash. So we will still keep after the SEH 5 knobs just to make sure. Then we will add the egg hunter. What the egg hunter is doing specifically, I will show you later in Immunity. Then we fill the rest with knobs again, times, and we adjust. -5, I already added this, minus the length of the egg hunter. For our second payload, we will just create a TCP reverse shell. I already executed this command here. I will use MSF Venom. The target platform is a 32-bit Windows. We will use a Windows reverse TCP shell. This is my attacking machine. This is the port I want to use. We will encode it. We will iterate the encoding 3 times. These are bad characters I don't want to have in our payload. So we have the null byte that would immediately disconnect our network connection, and these are the codes for carriage return, new line, new feed, and our output should be Python, so we can just copy paste. So we never forget what it was. It's good practice to document what it is. So our payload 2 will then be the newly created buffer, or that buff. It will be the new payload, payload 2. We have our eggs, we have the egg hunter. So let's save it. Let's prepare our target and walk through with the egg hunter and see what happens. Jump to our pop-up red to set the breakpoint. We start the program. Let's see. We have our multi-handler listening for the reverse shell. We could also just use Netcat, but I was just used to use the Metasploit console. Let's send it. We have our crash, Shift F9. We are at our pop-up red. We have our jump short, we are in our knobs, and this here is our egg hunter. So let's see, what is the egg hunter doing? So first, it takes the EDX register and makes sure we jump at the end of this page. Oops. So single step. Now we increase EDX by 1 to jump to the next page. We will push the address of EDX onto the stack, because when we later on perform our system call, this register will be set to Fs and we need to restore where we are. EDX right now acts as some kind of a counter. So we will increase EDX and start reading what is here. So we will go through each character, and we will check if this address is accessible for us, and then we will check if whatever is here is what we defined as an egg, so our WOOT. But let's do this step by step now. So we push EDX onto the stack. Now we push 2 onto the stack and we pop 2 into EAX. And now with int 2e, we would perform our system call. System call number 2 is the anti-access check and audit alarm. What it does here is it will check EDX if the memory address is accessible or not. I'm quite sure this function also normally would do something else or addition, but I have no clue what. But to understand an egg hunter, this is, I think, enough for now. It might also be that when you use Windows NT 2003, so an older Windows operation system, that you use system call 0x43, which is the NT-display string. This is a function used to display a string, usually on a blue screen, and this would also allow you to verify if a memory address is readable, accessible, or not. So we now conduct the system call, and what we see here is now that EAX became 5C. So here we can have 2 different values. If the memory address we just checked is accessible, it will give us a 5C. If the memory address is not accessible, we will just get the value of 5. And as you can see here, we do compare the lower bits of EAX with 5. In our case, we have 5C, so we can read the memory. What we do next is we restore our EDX, so we pop EDX, and if the value was equal to 5, we would jump back, we would increase EDX by 1, and we would try again. In our case, EAX is not 5, so we won't take the jump. What we do next is we take our egg, WOOT, and move it into EAX. We will move EDX into EDI. And now we will compare these 2 values. So we will compare EAX and EDI. The 0 flag is not set now. So jump if not 0 flag is set. So we will jump back, because this means EAX and EDI was not the same. It was not the egg we were looking for. We increase EDX by 1 and we repeat the same game over and over again. Let's do our system call. It's once again readable. So we don't jump. We put our egg in here. We move EDX into EDI. We will compare. It doesn't work. So we go back. We increase EDX and so on. So let's now set a breakpoint here, because otherwise it might take too much time. And we now just let the program execute. So now jump not 0, it was the wrong jump is taken. Sorry, we set the breakpoint here because we want to see what happens after this jump. So if the value in EDI matches with our egg. So let's continue. What you might see is, while the egg hunter is running, the CPU usage will go up to 100. So if you have a lot of memory or it just takes a lot of time, the CPU usage will go up to 100 while the egg hunter is searching. So we already hit our breakpoint now. Let's see what we have at EDX, follow and dump. Oh, sorry, EDI. So here we see our egg, and it's here for 2 times. So also the second scan is successful. We found it 2 times. So now, next what we do is we jump to EDI, because EDI will be our payload. We jump here and let's compare. It starts with BA87. So it's BA87. So I'm very optimistic that we will get a shell back now. Let's continue running. Function F9. Sending encoded stage. And here we are. We are on our target system. Okay, so I hope this tutorial was helpful for you to understand what an egg hunter is. If you got any questions, feel free to leave a comment or send me an email. And also feel free to give me feedback if you think my tutorials are a little bit too long, you want a shorter version, or if it's just the right size for you. Okay, one important thing I don't want to forget to mention is a big shout out to the awesome guys at Corlan and Fuzzy Security. So since I just give you a brief overview of techniques I use during basic exploit development, please make sure that you have a look at the Corlan website and the Fuzzy Security website, because they give you many more background information and they are a really good source to learn. Okay, that's it. Bye. See you next time.